Okay, Calc BC, Unit 3, Day 1 assignment out of your book. I thought instead of me writing all the stuff down, I'll just show you my work and explain it, and then hopefully that'll help you with any questions you have. So this is a review of some stuff from Calc AB. So these first problems, you're just doing the odds, so you should check in the back of your book already. It says identify each x value at which an absolute extreme value occurs. Explain how your answer is consistent with the extreme value theorem. Meaning, if you get absolute maxes mins, why does that make sense? If you don't, why does that not make sense? So this first one said I would say there's an absolute max at x equals b and a min at x equals c2. And this is consistent with the extreme value theorem because this the conditions in order to use extreme value theorem, that it's continuous and on a closed interval, are met. So makes sense. Problem 7, the absolute max value is c. Absolute min value, I guess we don't have a min value that we can specifically pinpoint. I mean, these are open dots, so it's not going to be at those. So but this makes sense. It's no closed interval, so can't use extreme value theorem. So it's okay that we didn't get absolute min. This one absolute max here at C, min at A. Extreme value theorem does not apply. That doesn't mean you can't get a max and a min in certain scenarios, but it's not continuous is the reason. It does have endpoints, and it is defined everywhere on a closed interval, but it's just not a continuous graph. Next problems, we're using analytic methods to find extreme values of the function on the interval and where they occur. So instead of looking at a picture like we did in the last ones, we're going to do the work algebraically. So we have endpoints, we have a function, we got to take the derivative, set it equals 0 undefined, to find your critical points. Now, we should try and use extreme value theorem as much as possible. So here's the work for that. I make a table. I plug these back into the original function. Now, I went ahead and cheated and used my calculator to get these decimal values. Sometimes we can get away without doing that and kind of estimate them in our head. But yeah. So let's see. So here's the absolute max and here's the absolute min. So the max is 1/4 plus natural log of 4 at x equals 4. So we're trying to actually find the extreme values. On problems 5, 7, and 9, we were just trying to find the locations, and we didn't really have information about the y values, but now we're actually looking for the extreme values. So we're looking for the y values and where they occur, which is generally a good just habit to make, where you identify the max and where it happens, and the min and where it happens. Also, we're looking for local maxes and mins. So we do have a local max at 1/2. 13, similar problem. We have endpoints. We take the derivative, we say equals 0 undefined. X can be -1, but it's outside the endpoints anyways. So we have no critical points. That doesn't mean we can't do extreme value theorem. We could plug them in a table, and it's got to be one of the endpoints. So that's the min, that's the max. Now, we could use the first derivative test to help us in some problems. On this problem here, it works because we only have one critical point between the endpoints. And so the fact that it's going down and then it's going up, and you get a relative min here, but that has to be the absolute min. But we can't use this first derivative test to identify absolute max because it's got to be one of the endpoints, and you just got to plug the values in. Now here, this one's going up the whole time, so we could actually use this to say, okay, well, that's got to be the absolute min, and that has to be the absolute max because it's increasing the whole time. So sometimes we can use first derivative test information to make some conclusions about maxes and mins, but I would avoid it unless you absolutely can do extreme value theorem. Okay, moving on. We got some more of these. Number 15, we're taking, we got endpoints, we take critical point, take the derivative, say equals 0 undefined. Find the critical points. There's multiple critical points. It's not uncommon with trig. Make a table, plug them all in. Now, if we did a first derivative test, we could identify relative maxes and mins, which we are, I guess, going ahead and answering on these problems. But as far as absolute maxes and mins, this doesn't tell us anything. I mean, absolute max would be either here or at this endpoint. Min is here or this endpoint, but you got to plug them in. You need to do a table. But we can use extreme value theorem, so plug them in, get our answers. There's the max, there's the min. The max is 1 at x equals pi over 4. The min is -1 at x equals 5 pi over 4. 17. This is one of those ones with rational exponents, which can get tricky for people sometimes. Take the derivative, set equals 0 undefined. X equals 0 is the only critical point. It's not a bounce because it's got an odd numerator. It is between the endpoints. So if you did a first derivative test, you could say, well, that's a relative min, and that's absolute min for sure. Now, maxes, we wouldn't know because it's one endpoint or the other. So we just got to plug these in. Now, I plugged these values in. Now, I don't know why. Oh, that's not a closed interval, so we can't technically use extreme value theorem. I mean, you could plug one in and see what it's going towards. And then, well, this is for sure the max, but there you go. Next problems. Find extreme values of the function where they occur. So same kind of questions. These ones have no closed intervals, so we technically can't do extreme value theorem. So you'll see that I'm kind of resorting to first derivative test and hoping that gives me enough information. So this one, if you take derivatives, say 0 undefined, find the critical points. There's only one, so it's decreasing, it's going down, and then it's going up. So this is a relative min, but it's also the absolute min. It's got to be lowest point, and there is no absolute max. 21. It's cubic. Take derivative, set equals 0 undefined, get a couple critical points, put them on a line check. This is increasing, decreasing, increasing. Now, the fact that this goes down forever over here and up forever here, there is no max, there is no min. So all we're going to get is relative maxes and mins, and we can tell what they are from this first derivative line check. 23, take derivative, set equals 0 undefined, get critical points. Now you got to be careful on some of these that there are domain issues. So you'll notice I did a little work here. I want to make sure the inside of this is always positive. So I set it equal that, and here's my domain. So any answers I get between -1 and 1 just don't make sense. That would be 0. I mean, I think you could still do kind of a line check kind of thing, and it should work out right. So if you tested 2, then that's positive, negative, positive, negative. It works, just doesn't make sense to even say there's any answers in this category. The sign change thing still kind of follows through and works out correctly. So, I mean, you could use it in your work, but this graph goes up forever over here, and then it goes down forever over here. So there is no max, there is no min. Well, yeah. I said the min is 0 at x equals -1 and 1. Oh, because this graph goes up forever and up forever. So there's no max, but if you plug -1 and +1 into the original function, guess what? They both give you the same value. So it turns out there is a minimum of 0. 25 potentially has some domain issues. So you see a little work over here. You can only give me answers between -1 and 1 for your final answer. Now, you might include these other areas in your work, but so we take derivative. Got to do a little chain rule there. So equals 0 undefined. We get all these critical points. Now, what we've decided over here from the domain is that -1 and +1 are technically not in the domain. Now, if you tested a value to the right where the domain doesn't exist, it still might work. If I plug 2 in here, ooh, actually, I get imaginary, so it doesn't help. So, probably don't want to test that. You could test like 1/2 or something. That'd be 1/4. That'd be 3/4. Positive, positive. It's positive, negative. So it's decreasing and then it's increasing. And at -1 and 1, you are getting vertical asymptotes. So the graph blows up, blows up. There is no max. The min is this point right here, which we're going to say is a solid dot. So that is your relative min, but it is going to be your absolute min. So that's 25. 27 has domain issues because it's a square root. So you want to make sure the inside is always positive. I'm trying to find my work here. But if you take derivative, set equals 0 and defined, you get these critical points. Now, where's my work for my domain? So x equal, I should have a line. Oh, there it is. There's my line check for this. And so -1 and 3, test 4. This is the domain. So I only can give answers between -1 and 3. And potentially including -1 and 3. So these are solid dots. Solid dot there. If we test over here at 4, this is where we get imaginary. So we really can't. We got to test here or here. So it goes down forever, down forever. So there is, but we do have endpoints. So -1 and 3. If you plug both those in, guess what? You get 0. So that's your min value. If you plug 1 in, you get 2. That's your max. It's a relative max, becomes an absolute max. 29. Now, doesn't seem like there's any domain issues there. I'm going to take the derivative, quotient rule, low d high minus high d low all over low squared equals 0 undefined. I get +1, -1. Now this, if you simplify it, you also get +1 and -1. So we don't get positive. The bottom is never equal 0. So the +1, -1 comes from the top right here. And as far as domain, we're good because this will never give you division by 0. So because x squared plus 1 is always positive. And so the whole thing's good. And so we're going up forever over here, down forever here. So there is no, I was going to say there is no absolute max or min, but I guess, I guess this approaches a horizontal asymptote. So this ends up being your absolute min right here. And this ends up being your absolute max right here. So I guess you got to be careful with that. I've always kind of thought, oh, it goes up forever and down forever. So it's going to go to infinity. Not necessarily. It could be going up forever towards a horizontal asymptote. So that's something good to watch out for. Okay, that was a little trickier. And then 31. 31 is kind of funky. So you're trying to find the extreme values. It's a function with a bunch of absolute values. Now, absolute values usually are, one way to deal with them is to rewrite them as piecewise functions. So when x is more than 2, then both of these are positive. You just drop the absolute values and it becomes this function right here. When you're between -3 and 2, this one is positive for sure. But this one can be positive or negative. Actually, no, this one will be negative for sure. So the way we do that is you change the absolute value by dropping them, but adding an extra negative. This one, you just drop them. And so then we can combine them together, and it's just a flat line. And then when x is less than -3, they're both negative. So the way we get rid of the absolute values is applying a negative to both of them, dropping the absolute values, simplifying it. What this graph looks like is this. It's kind of funny graph. So then we could take the derivative, which has all different kinds, and it equals 0 here only, which kind of makes sense as that flat part. And we have endpoints, which are given to us, -5 to 5. So we could make a table. And I guess we could plug -3 and 2 in, but it's really constantly 0 that whole time. So it's weird. It's not really like a critical point. It's more like a critical interval. But looking at this picture, the max has to be at one side or the other. And so if you plug 5 into this, you get an answer of 11. If you plug -5 in, you get an answer of 9. So that's your max. If you plug these two in, it's constantly 5. So that's the lowest point of the graph. It's a min along an interval, which is a little weird. So a set has a local max at -5, 9, which I would say is not necessarily true because I think this graph keeps going up forever, right? So I don't really like that answer, but there you go. It's kind of a weird one. 35, identify critical point, determine local extreme value. So, I mean, you're getting a lot of practice with absolute max mins, EVT. So this one here, there's your function. I went ahead and just took the derivative of it. And so I just did product rule. And then you want to maybe try and clean it up. So I went ahead and distributed this in here, and then I combine these like terms. You could then factor out the x to the -1/3, or you could rewrite it as a fraction and get the same thing. I think factoring out the x to the -1/3 is kind of handy. Either way, you're going to get a critical point at -4/5 and 0. So first derivative line check gives you this, and we don't have endpoints, so the graph goes down forever over here and goes up forever over here. So there is no max, there is no min, but there is a relative max, local max, and a relative min, local min at these points, and you could plug these values back in the original equation and get their values. 39 is piecewise function, so we could, this is a graph of it. So piecewise functions, sometimes I just find helpful to have a picture of the graph. So there's a picture of the graph, and there's just that one critical point there where the derivative is undefined because the slopes don't agree there. So that would be an undefined slope. It gives you a corner. So you do a line check with that. It's going up forever over here and up forever over here. So there is no max, but that's the relative min, which is also a absolute min. Because it's the only one, we can actually make that call. So there we go. And just a few more questions here. True, false. If FC is a local maximum of a continuous function on an open interval, then the derivative must equal 0. No, it could be a corner or cusp, but it could be undefined. Might be, it's not always true. 46, if M is a local min and M is a local max of a continuous function on an open interval A to B, then M has to be lower than capital M. The relative min has to be lower than the relative max. Well, relative is just relative for both of these. So here's just a quick example. They didn't say that that's the only local min, that's the only local max. So we might have other local maxes and local mins to where this local max ends up being lower than the local min. So they didn't say absolute. If they said absolute, then that would be true. 47, which of the following values is the absolute max of this function? So we're doing a quick EVT, take derivatives, that equals 0 and define, find the critical points. You got endpoints here, closed interval, plug them in. That's the absolute max is 10 at x equals 2. Don't be fooled. Don't pick B. Which of the following values is the absolute maximum? So they're looking for the y value here, not the location. Got to read it carefully. That's it. I hope that helped.